185 miles per hour. The pressure inside the eye is 890 millibars. On the 12th of April, in the western Pacific Ocean, satellite imagery from the Joint Typhoon Warning Center clearly shows something that should not exist in April. A perfectly symmetrical vortex spun up to the absolute limit of the Saffir-Simpson scale. Category 5. The most powerful tropical cyclone on the planet for the entire year of 2026. Write in the comments where you're watching us from right now, and we continue. Its name is Sinlaku. In the language of the island of Kosrae, part of the Federated States of Micronesia, this word means the goddess of nature and the breadfruit tree. A beautiful name. And it was assigned to a system that, in less than 24 hours, transformed from a Category 1 with winds of 85 miles per hour into a Category 5, a speed increase of 75 miles per hour in a single day. Such figures do not fit into the standard intensification model. Such figures force meteorologists to revise forecast cones in real time. And here is what is important to understand from the very beginning. This system was not heading into the open ocean. It was heading toward United States territory, not toward Florida, not toward Texas, not toward Louisiana, toward islands that most people in the continental United States have heard of at best once, when in October 2018, Super Typhoon Yutu passed through the same corridor and left behind a disaster area with a total power outage lasting several months. Saipan, Tinian, Guam, the Commonwealth of the Northern Mariana Islands, one of the most remote fragments of American territory in the western Pacific Ocean. 52,000 people on Saipan, 3,000 on Tinian, and not a single kilometer to retreat to. Sinlaku approached these islands on the night of the 14th of April. Radar on Guam recorded the inner eye wall passing directly over Saipan and Tinian, a narrow ring of maximum winds that brought sustained flows of 150 miles per hour. The National Weather Service issued an extreme wind warning, a phrasing that appears in bulletins only when damage is qualified as catastrophic. In NWS language, this word has a specific technical meaning. It means that structures not designed for such loads will cease to exist. And here arises the first question that defines everything we will talk about next. Not how strong the storm was. There is already an answer to that. But another one. Why a system of such power formed in April, months before the start of the peak typhoon season, in a zone where ocean conditions were not supposed to support intensification of this level so early in the year? The data we have today does not give an unambiguous answer, but it provides enough details to see the outlines of something much larger than a single storm. So we have a system that gained 75 miles per hour in a day and reached Category 5 in the middle of April. This fact in itself is already anomalous. But it becomes truly significant only if you look at what exactly allowed it to happen, and why standard explanations work only halfway here. When the Joint Typhoon Warning Center issued the first forecast bulletins for the system designated as 04W on the 10th of April, the baseline scenario assumed strengthening to Category 3, possibly Category 4, with an approach to the Mariana Islands in a weakened state. The models took into account standard parameters: ocean surface temperature, vertical wind shear, and mid-troposphere humidity. By all these indicators, conditions were favorable but not exceptional. The surface temperature in the system's path zone was 28 to 29 degrees Celsius. Wind shear was low, within 5 to 10 knots. These are good conditions. But not the conditions that usually breed monsters in April. And this is where the part of the story begins that a superficial review misses. The key factor that separated Sinlaku from an ordinary early season typhoon was not the surface temperature indicator. It was the ocean heat content indicator, OHC. This is a parameter that measures not a thin upper layer of water, but the total thermal energy accumulated down to the depth of the 26-degree isotherm. In Sinlaku's intensification zone, OHC was 125 to 150 kilojoules per square centimeter. For April, this value is typically characteristic of the peak months of the typhoon season, August and September. Why this is critical. When a tropical cyclone passes over water, it draws heat from the upper layer and triggers upwelling, the rising of cold, deep waters to the surface. This is a natural negative feedback mechanism. The storm weakens itself by cooling the water beneath it. But if the warm layer is deep enough, if D26, the depth of the 26-degree isotherm, is depressed dozens of meters below normal, upwelling does not reach cold water. The storm continues to receive energy. The negative feedback does not work. This is exactly what happened. Sinlaku passed over a section of the ocean where the warm waters were not a thin film on the surface, but a massive reservoir extending into the depths. The system received enthalpy flux from the ocean to the atmosphere practically without restriction, and converted it into wind kinetic energy with an efficiency close to the theoretical limit. According to data from the University of Wisconsin, Sinlaku came close to its maximum potential intensity, MPI, which for these conditions was estimated at approximately 175 miles per hour. The actual peak was 185. The system exceeded its own calculated ceiling, and this is not a detail for academic discussions. This is a signal, because MPI is not just a number, it is the boundary of the model. When a real storm goes beyond this boundary, the question is no longer how strong it is. The question is how accurately we understand the conditions in which it forms. And the conditions of April 2026 in the Western Pacific Ocean, judging by what we observed, differed from what models considered possible. Models showed a ceiling of 175 miles per hour. Reality showed 185. A difference of 10 miles per hour might look like a margin of error, but in the physics of tropical cyclones, it points to an energy source that the calculation did not account for. And this raises a question about the very place where it all happened. The Mariana Islands are the crests of an underwater mountain range extending in an arc for over 600 kilometers along the western edge of the Pacific Plate. To the east of this arc, the floor drops into the Mariana Trench, the deepest point in the world ocean, 10,994 meters, in the area of the Challenger Deep. This is a zone where the Pacific Plate subducts beneath the Philippine Plate at a speed of about 7 to 8 centimeters per year. Subduction here is active, seismicity is constant, and the interaction between lithospheric processes and ocean circulation is much less studied than is commonly thought. But for our conversation, it is not the geology of the bottom that matters. What matters is the oceanography of the upper 200 meters. The Mariana Islands are located within the North Equatorial Current, NEC, a powerful westward flow that carries warm waters from the Central Pacific Ocean toward the Philippines and further to the coast of East Asia. It is precisely in the NEC zone that the thermocline, the boundary between the warm upper layer and the cold deep layer, lies anomalously deep. This is a direct consequence of geostrophic balance. The westward current in the northern hemisphere maintains the tilt of the thermocline, deepening it to the north. The result is a massive column of warm water that does not dissipate during the passage of one storm and can fuel the next. A study published in early 2024 in Nature Communications showed that the NEC zone is the most favorable region on the planet for the rapid intensification of super typhoons, precisely because of the combination of high heat content and increased stratification, which minimizes the cooling effect of upwelling. Before this work, it was believed that the main zone of rapid intensification was the so-called eddy-rich zone further north, between 17 and 25 degrees north latitude. New data shifted the focus further south, directly into the corridor through which Sinlaku passed. But there is another layer. A separate paper published in February 2026 in the journal Atmosphere described systematically for the first time a mechanism that the authors called thermal rejuvenation. The essence is as follows. When sufficient time passes between two consecutive typhoons in the same region without storm activity, the upper layer of the ocean restores the lost heat. The longer the pause, the fuller the recovery, and the more powerful the next storm. The Western Pacific Ocean from January to early April 2026 was virtually free of typhoon activity. 3 months of silence. 3 months of continuous heat accumulation in the upper layer without a single storm to expend it. And into this charged environment on the 8th of April entered a disturbance that the JTWC recorded southwest of Chuuk. The ocean was waiting. It had plenty of energy. The question remained, who would get it? The energy went to Sinlaku, but not only to him. And this is where a single storm ceases to be a single storm and becomes an element of a configuration that meteorologists rarely observe, and which had not been seen in April for a long time. On the 8th of April, when the JTWC recorded the birth of the future Sinlaku north of the equator, on the other side, in the southern hemisphere in the Solomon Sea, another system already existed. Tropical cyclone Mila. It had formed a few days earlier and was behaving atypically, moving hardly at all, spinning in place like a top, while briefly gaining Category 4 intensity, which is a rarity for the Solomon Sea. Mila's track resembled a circle rather than a line. The system could not choose a direction. 2 cyclones, 2 hemispheres, 1 time window. In meteorology, this is called twin cyclones. Twin cyclones forming on both sides of the equator in response to the same westerly wind burst. The mechanism is well described. A powerful impulse of westerly wind in the equatorial zone creates rotation in both hemispheres simultaneously, clockwise to the south, counterclockwise to the north. The phenomenon is rare for the Atlantic, but more frequent in the western Pacific Ocean and the Indian Ocean. And every time it is observed, the same question arises. What next? Next is this. The westerly wind impulse that gave birth to Sinlaku and Mila, plus the additional easterly flow generated by the cyclones themselves, push warm water from the western Pacific Ocean toward the east, in the direction of South America. This is the beginning of a chain that oceanographers call the Bjerknes feedback loop. Warm water shifts to the east, convection intensifies over it, convection creates even more westerly wind, and the wind pushes even more warm water. The loop closes, and when it closes, El Niño forms. By May 2026, several forecasting centers, including NOAA, were already recording signs that the process had begun. Moreover, a phrasing appeared that is used with caution, Super El Niño. Not a confirmed diagnosis, rather a horizon of probability. But the very fact that this formulation entered professional circulation by the end of spring suggests that the April events were not a local episode. Meanwhile, Sinlaku left behind another trace that has nothing to do with destruction on the ground, but has everything to do with the scale of energy that the system released. The NOAA-20 satellite, equipped with the VIIRS instrument, recorded concentric waves in the mesosphere on the night of the 12th to the 13th of April, at an altitude of about 85 kilometers. Gravity waves generated by convection inside the typhoon and made visible by the airglow of the upper atmosphere. The storm in the troposphere deformed atmospheric layers located an order of magnitude higher. This is not a metaphor, this is data. A tropical cyclone that reached such power that its energy footprint is read not at the cloud level, but at the edge of space. Gravity waves at an altitude of 85 kilometers are a scale of energy, but energy recorded by a satellite is an abstraction. Energy that reaches the ground is concrete, and it arrived on the night of the 14th of April. Sinlaku approached the Mariana Islands already past its peak. By this time, the system had weakened from 185 to 150 miles per hour, formally to the upper limit of Category 4, but it slowed down to 5 miles per hour of forward speed. For an island that cannot be left, a slow typhoon is not a relief. It is prolonged destruction. The inner eye wall passed over Saipan and Tinian not for minutes, but for hours. Radar on Guam recorded the eye structure superimposed directly onto the outlines of the islands, with a characteristic band of missing data where the terrain blocked the beam. By this time, the NWS was already using the phrasing extreme wind warning. In the practice of the National Weather Service, this category is applied when sustained winds exceeding 115 miles per hour are expected in a populated area. It means one thing: shelter in place, without moving, without evacuation, because there is nowhere left to evacuate to. And here the story of Sinlaku intersects with a story that had already been told 8 years earlier, and which, judging by the scale of the damage, was not learned. October 2018, Super Typhoon U2, Category 5 with winds of 180 miles per hour, a direct hit on Tinian and the southern part of Saipan. Total power and water supply shut down, destruction of thousands of homes. Children attended school in tents months later. The mayor of Tinian said then, "Critical infrastructure is compromised. Ports are inaccessible. There will be no electricity for months." According to data from the Government Accountability Office, recovery took years, and the island's economy, already weakened after the collapse of the textile industry in the previous decade, never returned to its former indicators. Sinlaku passed through the same corridor, literally. The trajectory is almost identical, northwest through Tinian and Saipan. And it arrived at an infrastructure that still bore the marks of the previous strike. The consequences looked appropriate. Trees were uprooted, power lines collapsed, roofs were torn off residential houses and commercial buildings. In the Garapan area, the central part of Saipan, water flooded homes and streets. On the territory of the Marianas Beach Resort Complex, a generator room caught fire during the storm. Fire crews worked in hurricane-force wind conditions. Saipan International Airport recorded 5.73 inches of rain on the 14th of April alone. This is one of the 10 wettest days in the entire history of observations. Over 9 inches fell on Guam. More than 1,000 people were placed in emergency shelters. 43,000 remained without electricity. On the 17th of April, the federal government declared a public health emergency. FEMA reported the deployment of 90 personnel and the pre-positioning on Guam of 1.1 million liters of water, 723,000 ready-to-eat meals, and 78 generators. By early May, electricity on Saipan and Tinian had still not been fully restored. Water supply on Saipan was working for half of the consumers. Half of Saipan without water 3 weeks after the strike. Electricity that has not returned, and a question that hangs outside the framework of humanitarian summaries. If this happened in April, what awaits these territories when the real season begins? Because Sinlaku was not a seasonal storm. It arrived 3 to 4 months before the statistical peak of typhoon activity in the western Pacific Ocean, which falls in the period from July to November. And it was not the only early signal. Let us return to the chronology. At the end of February 2026, Cyclone Horatio formed in the southern Indian Ocean and reached Category 5. It was the first cyclone of such power in the year. Then, in early April, Mila in the Solomon Sea, briefly reaching Category 4, and almost simultaneously, Cyclone Waianu, which crossed the North Island of New Zealand on the 12th of April. 3 systems in the southern hemisphere plus Sinlaku in the northern hemisphere. 4 tropical cyclones of significant intensity in a window that is usually considered transitional, off-season, and relatively calm. According to data from the Climate Adaptation Center, the April 2026 configuration, 2 cyclones in the southern hemisphere and a super typhoon in the northern hemisphere, was qualified as a rare triplet pattern. Not unprecedented, but rare enough to attract the attention of those who track not individual storms, but systemic states of the atmosphere. And all this was happening against the background of ocean temperatures that continued to exceed the observed norm. Since April 2023, that is, over the course of 3 years, global ocean surface temperatures have been in a zone that Climate Central describes as continuously higher than any previously recorded period. This is not a short-term anomaly. This is the new background. And against this background, storms form that find more energy in the ocean than forecast models put into their calculations. A separate line of data is the NOAA forecast for the Eastern Pacific for the 2026 hurricane season. It was published in May and contained an estimate, a 70% probability of an above-normal season. The main factors are the weakening of vertical wind shear in storm formation zones and elevated surface temperatures. Both factors are directly linked to the development of El Niño, signs of which were already being recorded instrumentally by this time. Correlation does not imply causation. This is worth repeating. The simultaneous existence of several powerful systems in different basins does not prove a single mechanism. But it means that the planetary energy budget, the total amount of heat available to the atmosphere and ocean to generate extreme events, in the first quarter of 2026 was at a level that allowed such events to be supported simultaneously, at several points, earlier than the usual calendar window. And this is the framework in which Sinlaku ceases to be the story of one typhoon. It becomes a point on the map where there turned out to be more points this year than expected, and the season was only beginning. There were more points on the map than expected, and the season was only beginning. This is an observation, not a forecast. But it is from observations that the picture is built, which is worth considering as a whole, stepping back a pace from each individual event. Here is what we have as of today. An ocean that for 3 consecutive years has held its surface temperature beyond everything recorded instrumentally prior to 2023. A warm layer that in the north equatorial current zone lies deeper than the climatological norm, forming a reservoir of energy inaccessible to the standard storm self-limitation mechanism. 3 months of silence in the western Pacific Ocean from January to early April, a pause during which the upper layer restored the heat expended by the previous season and accumulated in excess. Twin cyclones on both sides of the equator that triggered a westerly wind impulse which, according to estimates by several research groups, is accelerating the formation of El Niño. And a super typhoon that exceeded its calculated potential intensity by 10 miles per hour, seemingly a small figure, but behind it stands a question about the accuracy of the very models we rely on. Each of these elements individually has an explanation. A warm ocean is the result of long-term heat accumulation. A deep thermocline in the NEC zone is a consequence of geostrophic balance. A pause in storm activity is a normal seasonal variation. Twin cyclones are a known, though infrequent, phenomenon. Exceeding MPI is a possible result of local mesoscale processes that are not resolved in global models. All this is true. And all this, put together, paints a picture in which a combination of explainable factors created conditions that go beyond the explainable. This is not a paradox. This is a property of complex systems. Every component is within the norm, but their simultaneous coincidence is outside the norm. Climatologists call this a compound event. The danger of compound events is not in individual parameters, but in their superposition. And the main problem is that forecasting systems, as a rule, evaluate each parameter in isolation. At the time of recording this episode, no agency had qualified the 2026 season as anomalous as a whole. This is a correct position. Data for a few months is insufficient for such a conclusion. But the same agencies record parameters that point to an increased potential for extreme events in the coming months. NOAA explicitly points to the probability of an active season. El Niño forecast models converge on the fact that formation has begun. Ocean temperatures are not decreasing. And here is the question to which science does not yet have a consensus answer. Is what we are observing part of a new, stable regime in which early Category 5s cease to be an exception? Or is it a statistical outlier that will be corrected in subsequent years? The difference between these two interpretations does not define an academic discussion. It defines how territories like Saipan and Tinian must prepare, for whom the next strike is a question of when, not if. When is a word that changes everything. Not if it happens again, but when it happens again. And for 52,000 people on Saipan, this is not an abstraction. This is a calendar in which July has not yet arrived. Sinlaku is gone. By the 20th of April, the system had completed its extratropical transition and was declared dissipated. On satellite imagery, nothing was left of it, an ordinary frontal vortex dissolving in the middle latitudes of the Pacific Ocean. But on the ground, the story continued. In early May, the Red Cross reported that hundreds of personnel from various states were still working on the islands. Electricity, partial. Water supply, partial. The only hospital on Saipan suffered from flooding. Several large hotels lost their backup generators. Roads are not all cleared. And in parallel, by the end of May, the next system was already forming in the Philippine Sea. Typhoon Jangmi, Category 1 on the Saffir-Simpson scale, broad, slow, with heavy rainfall. It did not reach the Mariana Islands, but it confirmed what the data had been showing since April. The basin is active, conditions for cyclogenesis persist, and the warm season is gaining momentum according to a schedule in which the starting point is shifted earlier than usual. We work with open data. Everything discussed in this episode is based on JTWC bulletins, NOAA publications, NASA satellite data, peer-reviewed studies, and expert assessments that are available to everyone. Interpretations and links between events are analytics, not a scientific consensus. We do not make predictions. For up-to-date information on preparedness and safety, NWS, FEMA, local emergency management agencies. But here is what is worth fixing in memory. In April 2026, a tropical cyclone that originated in a zone where the thermocline is depressed deeper than normal, where the ocean accumulated heat for 3 months without a single storm, where the geostrophic balance of the westward current created conditions going beyond average seasonal parameters. This cyclone turned from a Category 1 into a Category 5 in a day, exceeded its calculated ceiling, generated gravity waves at the edge of space, struck a territory that had not yet recovered from a previous strike 8 years prior, and became part of a planetary configuration accelerating the formation of a potentially extreme El Niño. And all this before the start of summer. It is now June. The peak months of the typhoon season are August, September, October. The ocean continues to accumulate heat. The Bjerknes feedback loop, triggered by the April twin cyclones, continues to operate. Warm water is shifting to the east. Convection is intensifying. Data for recent weeks is not yet sufficient to say what the next storm will be like. But the data is sufficient to say that the environment in which it forms is already charged. Saipan knows this. 3,000 people on Tinian know this. The question is whether anyone else knows it.